We have certainly spent a great deal of time studying the structure of a lossless transmission line with a passive load attached to the end. We went through and applied boundary conditions and found the solutions with respect to the telegrapher equations. We then looked at many special cases in terms of the load, real, imaginary, and so forth. We looked at special cases of the transmission line length and its effect on the input impedance, the resulting input impedance. We talked about the relationship between the load impedance and the input, the reflection coefficient, load reflection coefficient, and the input reflection coefficient. And we studied this tool called a Smith chart that allowed us to determine relatively quickly the relationship between the load impedance and the input impedance. At this point in most studies of transmission line theory, again, we start with the two-port device, the transmission line, the telegrapher equations. We connect a passive load to one end and study what happens there and the resulting input impedance, as I said. And then the last step is to connect a source on the other end, and then finally complete the circuit and able to determine the voltages and currents unambiguously at every point along the transmission line. But I'd like to do something a little bit different. I would like to, instead of now attaching a source to the transmission line that's terminated, we're going to take off the load, and we're going to connect a source to the beginning. So again, we're going to be looking at a structure, a transmission line, that has connected at one end, at one port only, a device. Instead of the device being a passive device, a passive load, this device now is going to be an active source. And so this is the structure we're going to look at here. The question, of course, is what is connected to the other end? Well, at this point, we will leave that unstated and unknown, just like when we studied the terminated transmission line. We never said anything about what source was connected to the beginning of the transmission line. We're not going to talk about what is connected to the end of the transmission line in this particular case. We're going to look at the boundary conditions that arise from this structure and the ramification of those boundary conditions. So we start with the transmission line, then we have a transmission line terminated load. Now we have a transmission line that is terminated, that is connected at a source at the other end, and then finally we'll put all those pieces together, and hopefully the result will make more sense having examined the problem in this way. The telegrapher equations, of course, still apply for a transmission line or telegrapher equation solutions. And here they're written in terms of the two unknown wave amplitudes, V0 plus and V0 minus. When we connected a passive load to one in the line, we were able to find, using boundary conditions, a relationship between V0 plus and V0 minus when the transmission line is terminated by a passive load. What we want to attempt to do now is again use boundary conditions to go through and find for a case of a source connected to a transmission line, find the relationship between V0 plus and V0 minus. And what we'll find, it's very different than what we had for a terminated transmission line because, of course, we have a very different device that is connected to our transmission line. Now, the important values in our analysis are going to be the value of the total voltage along the transmission line when evaluated at the location where the source is attached. So we look at our index Z, we see it's increasing as we're moving from left to right as it normally is. But in this case, the source is attached to the beginning of the line here, and we'll call the index for that location ZG, this purple ZG. Again, this is just a number, an index. It could be anything. Oftentimes, it's a value equal to minus L, the length of the transmission line. But of course, in this case, we don't know what the length of the transmission line is. We want an answer that's independent of that length. And so, again, we'll just denote it as a arbitrary value, purple value there of ZG, a numerical value. So we take that number and we put it into our telegrapher equation for current, total current, and that will pop a complex number, and that complex number will represent the current right here at the beginning of the line. Likewise, for total voltage, we'll evaluate it at this numeric value ZG, and what will result is a complex number that represents the total voltage right here at the beginning of the transmission line. And those values are what we're going to use to apply our boundary conditions. This then is the mathematical representation of those two complex numbers. Notice they depend on the unknown wave amplitudes of V0 plus and V0 minus. So we evaluate the total voltage at the beginning of the line and the total current at the beginning of the line. Again, this is not a function of position Z. This is a statement of a function that is specifically evaluated at the line index location ZG. In addition to the math related to the transmission line, the telegrapher equations, we also have a mathematical statement here that describes the source. And in this case, it relates the parameters of the source, the device parameters, in this case, VG, the open circuit source voltage, and ZG, the source impedance. And we relate those two device equations to the voltage and current at the output of the source, which I will denote as Vn and In, as they are the voltage here at the input of the transmission line and the current In flowing into the input of this transmission line. Now to apply our boundary conditions, and they're fairly simple, essentially the same boundary conditions we applied with respect to analyzing a terminated transmission line. The first of the boundary conditions, we use KVL, and that relates the input voltage, the voltage that results at the output of the source, to the voltage at the beginning of the transmission line. And so we come up with this mathematical statement: Vn is equal to the total voltage when evaluated at this location on the line. And again, I emphasize that because students oftentimes will tell me the input voltage is equal to the total voltage function, a function of line index Z. And of course, that doesn't give us a boundary condition. What we're saying here is one number has to be equal to another number, and this is only a number, a complex value, when we in fact evaluate it at the position on the transmission line here where the source is attached. Same thing for the current. KCL tells us the current flowing into this transmission line must be equal to the current right here at the beginning of the transmission line. Remember, the current further down here will be different than the current at the beginning. The current further down still will be different than current at the beginning. The same thing for voltage at the beginning of the line will be different than the value of the line voltage if I move some distance down the line or another distance still. So it's not as if the current is a constant with respect to position. That's hardly the case, nor is it the case that the voltage is a constant with function of position. So we need to make sure that we evaluate the current, total current, right here at the beginning of the line, likewise the total voltage, and only then can we apply KVL and KCL. We can get out our algebraic pencil and go through and try to come up with the relationship between the unknown wave amplitude V0 plus and V0 minus. And so we take our device equation for our source, and now by KVL we know Vn is equal to the total line voltage evaluated at the beginning of the line, and then we add to it this term, which is the total input current. It must be equal to the total line current at the beginning of the line, and multiply that by Zg, and we get this term. And then we go through and collect terms, and notice we have one term that's proportional to V0 plus and another term which is proportional now to V0 minus. And what we're going to do is find a relationship between those two unknown wave amplitudes. Now for a terminated transmission line, we found the relationship of V0 minus in terms of V0 plus. For the source, we're going to go through and do it the opposite way. We're going to determine a representation, an expression for V0 plus in terms of V0 minus. And V0 plus, of course, is the wave amplitude, the complex amplitude of the wave propagating in the direction of increasing z. In other words, the wave amplitude of the wave that is coming out of the source and propagating down that transmission line. And when we do the algebra, we get this result here, which looks a little bit stressful to look at. It's not like we got for the terminated transmission line with a load at the end. There it was fairly simple, the relationship between V0 minus and V0 plus. Here it is certainly much more complex, much more mathematically rich. The important thing and the key thing here is we have two terms. And so no longer do we find that V0 plus is proportional to V0 minus. In fact, if we look closely, we see this first term is dependent on VG, the open circuit voltage source of the source, and then the second term is dependent on V0 minus. Since we now have an expression for V0 plus in terms of V0 minus and open circuit source voltage VG, we can then write explicitly the function for the plus wave voltage, the voltage of the plus wave, the wave propagating in the direction of increasing z. Write that in terms of the position index z, lowercase z. And so we do the math there, and this is the result that we get. If we look closely here, here is the index z. So this term here depends on our position. And it's basically a phase term. So the phase of the plus wave will change as a function of position. But of course we know that to be true. The magnitude of the plus wave along a transmission line is always has a magnitude that is constant with respect to position. The phase alone is changing. And it's changing in a way as the minus wave or the plus wave we know always does. It changes in a way such that the index is proportional to a minus beta. So then this provides us with the magnitude of the plus wave. Notice this term is not dependent on the index, the position index z. It depends instead on the parameters of the source that is attached to the transmission line, VG and ZG. Likewise, it is dependent on the transmission line characteristic impedance, Z0. And then finally, and most importantly to note, it is dependent on the value of the minus wave voltage when evaluated at the beginning of the line where the source is attached. The minus wave voltage. And so we see that the minus wave voltage, the voltage that is moving down back from the source back from the end of the line, back toward the source, that minus wave voltage, if we had a load down there, we would say it's the reflected wave, it affects the plus wave voltage. What's coming back toward the source affects what's coming propagating outward from the source. And that's a very important point. Often students think of the plus wave voltage, the voltage associated with the wave that is propagating from the source down the transmission line toward the load. We think that plus wave voltage is due to the source and the source alone. Now certainly, as we've just seen mathematically, it does depend on the source. But also, as we've seen mathematically, it depends on the minus wave, the wave that is reflected from the load at the end of the line that is propagating back toward the source. And so we have a situation, we can't say that the plus wave is created by the source and then that plus wave reflects off the load and the minus wave then is created from the plus wave. The source creates the plus wave reflects from the load and creates the minus wave. That's sort of our causal thought process. But that's actually not the case. What we have is a very circular process. The plus wave propagates down the line, it reflects on the load, but the reflected wave propagates back toward the source and it interacts with the source in a way that then affects the plus wave as it propagates down the line. If you're familiar at all with bounce diagrams, and some of you may be on transmission lines where we take an impulse and we see that first it propagates down the line, it bounces off the load, comes back to the source, bounces, comes back to the load, back and forth each time modifying the function, the wave at each reflection. And The important thing to keep in mind then with respect to those bounce diagrams is all the math we're doing with respect to transmission lines is sinusoidal, steady state analysis. Those sine waves, those complex exponentials that we have been on forever and will be on forever. So we have reached steady state. You've bounced around back and forth between source and load so many times that we've reached a steady state solution. And that steady state solution is a solution that will satisfy the boundary conditions on either end of that transmission line. And so we, again, cannot say that the plus wave creates the minus wave or the minus wave creates the plus wave. They each interact with each other. And the previous equation that we showed relating V0 plus to V0 minus and the source voltage VZ is really a statement of the mathematical coupling between all of those phenomena. To see this more explicitly, hopefully, let's evaluate the plus wave voltage. We determine the expression for the plus wave voltage and evaluate it specifically at the location at the beginning of the line where the source is attached, at this index purple ZG, whatever that value happens to be. Notice this value is not equal to V0 plus. V0 plus is the value of the plus wave voltage when evaluated at the index location Z is equal to 0. And generally speaking, this ZG will not be 0. And so we get this simple result, but because we know what V0 plus is in terms of VG and V0 minus, we can rewrite it in this form. And what we see here again is there are two terms. And it's important to look at these two terms and what creates each of those two terms. The first term in that expression is dependent on the open circuit voltage of the source, the generator voltage VG. The second term in that expression depends on this minus wave voltage when evaluated at the beginning of the line where the source is attached. And so we can think about the resulting voltage, V plus, at the beginning of the line, right there where the source is attached, as being a result of a superposition of two phenomena, one involving the open circuit source voltage VG, and the other involving the minus wave voltage V minus at that location. And so we're going to rewrite the expression that we achieved on the previous page in terms of the plus wave voltage at the beginning of the transmission line into two terms. I'll call it VA and VB. VA is the voltage due to the open circuit source voltage, and VB is the voltage due to the reflected wave V minus at the location where the source is attached. What I want to show here is each of these two terms make physical sense. We can determine their mathematical structure, their expression, if we go through and apply superposition. How do we apply superposition? Well, if we have two sources, two things that are a stimulus on a circuit, we can go through and turn off all but one and determine the analysis, the result for that one circuit, and then turn off that source and turn back on the second, and then determine the analysis or the result from that second source. If the circuit itself is linear, we could add those two results together, and that would be the total stimulus, the total result. And of course, we did this for great effect when we talked about transimpedance parameters and transimpedance parameters, for example. But in this case, we're going to look at the two sources as being the open circuit voltage VG and the minus wave voltage evaluated at the beginning of the line. That minus wave voltage is going to be the source that we turn off first. Let's say the value happened to be 0. And let's look at the circuit if the minus wave voltage is equal to 0 and see if we can figure out what the resulting plus wave voltage would be in that case. Well, one thing we know from our analysis on our transmission line is that if we have no minus wave voltage, that the line impedance is going to be Z0 at every location. Remember, we have a situation where the line impedance is the ratio of the total voltage to the total current. But if the minus wave voltage, or if there is no minus wave, then the minus wave voltage and the minus wave current are equal to 0, and therefore the line impedance is simply the ratio of the plus voltage to the minus voltage, which we know defines the characteristic impedance of the transmission line. So again, if we have no minus wave voltage, the line impedance is Z0 at every location on the line, and that includes the beginning of the line where the source is attached. The input impedance is equal to Z0 when the minus wave voltage is equal to 0. And so in that case, we know the plus wave voltage is simply equal to the total line voltage. Remember, the total voltage is the plus wave voltage and the minus wave voltage added together. Well, if the minus wave voltage is 0, the total voltage, therefore, it consists only of the plus wave voltage. So we're going to use these two facts which occur because of this statement. So we can rewrite our circuit in this way. We're going to take our transmission line and replace it with its input impedance. In that case, that would be Z0. And so we have a simple voltage division problem. We know that the voltage from this location to this location, the voltage at the input of the transmission line, the voltage at the output of the source, then, is simply equal to VG times the ratio of Z0 divided by ZG plus Z0. That value right there, that is voltage division. And that provides the voltage from here to here. Now that's the total voltage at the beginning of the line at ZG, but because the minus wave voltage is equal to 0, that total voltage is likewise equal to the plus wave voltage. So the plus wave voltage at the beginning of our transmission line is going to be equal to this when we have no minus wave voltage. Only when we have no minus wave voltage is this expression true. Well, that plus wave voltage, when this is true, was by definition what we called VA, our first term, the voltage of a plus wave that is due to the source voltage VG and the source voltage VG only, since the minus wave voltage of the second term is set to 0. And we see that result is, in fact, dependent on VG and VG only. This result is the first term that we had in our plus wave voltage expression for the beginning of the line. Remember, this is the first term, and then this is the second term. This is our VB plus that we had. Again, we set this equal to 0. This term goes away, and we're left with this, which is exactly the result we got by circuit analysis. So the result we got there makes sense based on our knowledge of our transmission line behavior. And that's the point I'm trying to make. This we got by just doing a bunch of algebra on our boundary conditions. But this term we see makes sense based on the fact that if V minus is equal to 0, then the total voltage is equal to V plus, the input impedance is equal to Z0 in that case, and we can solve for this directly using a simple voltage division. To complete our superposition, we are going to turn back on the minus wave. We're not going to assume the minus wave any longer is 0. We're going to assume it is some non-zero value that is propagating toward the source in the direction of minus Z. But we are going to turn off the open circuit voltage source VG, and by turning it off, setting it equal to 0, again we have this circuit equation VG is equal to 0 for a voltage source. Well, that is the definition of a short circuit, so we're replacing our voltage source there, our ideal voltage source, with a short circuit. And this is the resulting circuit that we get. And it looks very much like a terminated transmission line. It is. At this point, it is a transmission line terminated in a passive load. The total voltage that we get at that location, we'll denote it as VB. Again, this is the voltage due to the minus wave and the minus wave only. That's therefore it has the subscript B. This total voltage now depends on both the plus wave, the voltage manifested by a wave propagating in the direction of increasing z, and the minus wave, the wave that is a voltage manifested by a wave that is propagating in the direction of decreasing z. And both these waves now we assume to be non-zero. The minus wave voltage will create this plus wave voltage V plus, and since both are present, then they must be added together to determine the total voltage here at the beginning of the line. Again, this looks like very much like a terminated transmission line problem, and it is, but there is one slight mathematical artifice that you need to be aware of and be careful of. So we have a terminated transmission line, a transmission line that is terminated in a passive load, and we have a wave that is now incident on that load, a wave that's propagating down to that passive load. But the key thing here to bear in mind is the wave that's propagating toward this load, the wave that's propagating in this direction from right to left, is the minus wave. It is a wave that's propagating in the direction of decreasing z, and by definition, any wave that propagates in the direction of decreasing z is the minus wave, and alternatively, in the direction of increasing z, we would call that the plus wave. Now, normally the passive load is terminated at the other end of the line here on the right side, and so the plus wave is the wave propagating toward the passive load. We say the plus wave is incident on that passive load. Likewise, the wave that's reflected from that passive load is propagating back away from the load, and therefore in the direction of decreasing z, and therefore we have the minus wave. Plus wave is incident on the load, a minus wave is reflected from the load. That is true if the load is connected here at the end of the line where the value of index z is the greatest. But in this case, we have a passive load that is connected here at the beginning of the line, at the location where the index z is its least value. And so the wave that's propagating down toward that passive load is propagating in the direction of decreasing z. It is the minus wave that is incident now on that load. And so we have to think through the results we got for a terminated transmission line. To what extent were those results associated with an incident wave and a reflected wave, and to what extent were they associated with a plus wave and a minus wave? Well, hopefully we know the answer, because the index that we set up, what we call plus and minus, depends on the direction of that index, which is purely a human artifact that we arbitrarily decided. The transmission line does not know or care in what direction we decided to make our index z, which increasing from left to right or right to left. What does matter is what wave is incident on the load and what wave is reflected on the load. So all of the results we had need to be keyed to what is the incident wave and not what is the reflected wave, not what is necessarily the plus or minus wave and what necessarily is the minus or plus wave. And this just shows that the wave that is reflected from this load, this source impedance, and again, now it's a passive load since this voltage is turned off, the wave that is reflected, that is propagating away from this passive load, is the wave that's propagating in the direction of increasing z. That is our plus wave. The plus wave is reflected from this load. The minus wave is incident on this load. Again, exactly opposite when we had from the condition when we had a load on the other end. So we can convert this load impedance, this source impedance ZG, into its reflection coefficient value, its load reflection coefficient value, and it's simply that impedance minus Z0 divided by that impedance plus Z0. The fact that now it is called ZG and ZL makes no difference with respect to the result we get, but we'll go ahead and call this gamma G to give you a different notation from the usual gamma L that's there. But again, this is the same as the gamma L we get for a passive load that is connected to the end of a transmission line. And we know that this value relates the incident wave at that load to the reflected wave at that load. That the reflected wave is equal to the incident wave at the load location times that, quote, load reflection coefficient, now we call ZG. Again, this is where students run into trouble because the incident wave at the load is the minus wave for this particular case. The wave propagating toward ZG, toward the source, is the wave propagating in the direction of decreasing Z, and therefore is the minus wave. The minus wave is incident. We multiply it by the load reflection coefficient, gamma G, and that gives us then the value of the reflected wave at that load location. The reflected wave here now is propagating back up the transmission line in the direction of increasing Z, and so we call that V plus. And so the V plus, the wave that is propagating in the direction of increasing Z, is the wave that's reflected due to this incident wave, the minus going wave, essentially the source wave in this second term. And so this is the result that we get. And we got this result simply by turning off the ideal voltage source, VG, and then analyzing the resulting circuit. And we recognize it as a terminated transmission line. We had to go through and change our notation a little bit because the incident wave was the minus wave and so forth. But we knew this is the answer that we get. And the point here is this answer, which we know is the right answer when our VG is set to 0, is the second term now in the expression for the plus wave voltage at the source location. This term we got from applying a voltage division when we set V minus equal to 0. This term we got by applying our boundary conditions of a wave reflected from a passive load when we set Vg equal to 0. We add the two terms together, and again, they both make physical sense. And so we see there are two mechanisms that create the plus going wave outward from our source in the direction of increasing Z. One term is due to the source itself, and the source itself only, Vg and Zg. The other term is dependent on a wave that is reflected from the source. The minus wave coming back from the load at the end of the line comes up, hits our source, and then part of that is reflected back down up the line, or down the line in the direction of increasing Z toward our load. So there's two mechanisms there. Energy that's being put in by the source itself, and energy that's propagating down because it's reflected off that source, and both are represented in this expression. Again, we got it with boundary conditions and a little bit of algebra, but we look at the result and we see that it makes perfect physical sense, and in every way it's consistent with what we know about how transmission lines and circuits behave. Rewriting that expression again, the total plus wave voltage at the beginning of the line has two terms. One term which is dependent on the source itself that's attached to the beginning of the line, Vg and Zg, and again a second term that is dependent on the minus wave voltage, the voltage that is coming back up the line from the load and interacts with the source to create a secondary component of the plus wave. We can tidy up these mathematics a little bit if we go back and use our definition of the source reflection coefficient and insert it into this equation, and we can rewrite it in terms of gamma g in this way, and it's a little bit more compact and straightforward perhaps by doing it that way. Now, in the end, you will probably never use either of these equations. We're never going to take values and put in there and calculate for the value of V0 plus. Why is that? Why did I show these equations then if we're never really going to apply them to solve a problem? These equations, and of course that's really what we're doing when we come up with the mathematics. The mathematics is the language of engineering and physics. The mathematics explain to us what's going on and confirm what's happening in the circuit based on principles that we know. And definitely that's the case here. We derive this so we can show that the plus wave is dependent on two terms, one of them most explicitly being the V0 minus term. And so so there is a situation, and again, this is what the important point of all of this is. Instead of saying that the source at the beginning of the line, it creates the plus wave propagates down, reflects off the load at the end, that creates the minus wave, which then propagates back up the line the other direction. That sort of sequence of causal events is not complete, because the minus wave that is created from reflecting off the load will then propagate up the line and then strike the original source, which will then reflect and create a new component to the plus wave. And if we add an infinite series of those, we will converge to our steady state solution, which is represented by this math. Again, we cannot say the plus wave creates the minus wave voltage any more than we can say the minus wave voltage creates the plus wave voltage. They both act together. They're coupled together in a way that requires them to, in order to satisfy boundary conditions at both ends of the transmission line. Now, one last thing I want to point out. I'm always a little bit worried about defining this term in terms of gamma G. Remember, gamma G came into play when we turned off our source voltage, VG, and only then could we define or use gamma G. Once we turn our source back on, even though mathematically we can define this value in this way, it's important to note that when we have a source at the beginning of the line, if we evaluate the reflection coefficient at the beginning of the line, we will not get a value of gamma G. Why? Because the source does not consist only of a load. It also has an ideal voltage source there, or only an impedance, ZG, I should say. It'll also have an ideal voltage source there. Yes, at the other end of the line, where we have a passive load, the boundary condition is the reflection coefficient evaluated there will be equal to the load reflection coefficient gamma L. But we can't go back to the beginning of the line and evaluate the line the reflection coefficient function there and claim it to be equal to this value gamma G. It will not be so. So be careful and don't try to apply that boundary condition to a source that has both a source impedance and an ideal voltage source, VG.